In the previous video, we have seen Fredholm's first theorem. We have stated the theorem. The theorem says this universal equation of second kind, that is the non-homogeneous Fredholm equation, will have a unique solution given by this y of x equals to fx plus lambda integral gamma x lambda f dt, and this gamma is a meromorphic function. And the question was to check what is meromorphic function of a complex variable. And then the gamma x lambda, that is your resultant kernel, is a dxt lambda from d lambda, and then we check what is dxt lambda and d lambda. And then afterwards we have denoted this by C1s, the small ci's and capital Ci's, and then we have seen the recurrence relation between small c's and capital C's. And after that, we have seen one example where we have found this capital C and small c. Then we have got these values of dx lambda and d lambda, and then we have found the resultant kernel and the solution. And some problems are given to check or to find the resultant kernel. And of course, if we have this resultant kernel, easily we can get the solution, right? And we are we said that the integral equation is a non-homogeneous integral equation. Alright. The reason maybe you can work out from here. If it is a simple thing, you can say if it is homogeneous, then you can put that fx is equals to 0 here and fx equals to 0 here, and then you have yx equals to 0. That's a simple observation we can say. Today we will see another example by using Fredholm's determinant. Briefly, I will give you the values using Fredholm's determinant. That is your equation 1 and 2. Those determinants involved in that. Find the resultant kernel when unit test kernel k x comma t is x into b raised to t. The value of a is 0 and the value of b is 1. Let's solve this. Then first you can check the solution and then you verify your solution. Now we have your right. We have the resultant kernel gamma x t lambda, which is given by d x t lambda upon d lambda. Okay. And then let me write what is dx lambda. So for you, dxt lambda is given by a x comma t plus summation t from 1 to infinity minus lambda raised to p divided by p factorial, and then we have this cp x comma t, and p lambda is 1 plus summation p from 1 to infinity minus lambda raised to p divided by p factorial, and then we have this small p. Small c. Again, for the CPs and small c and capital C, we had those integrals and determinants. Let me write those also. We had this determinant k x x1 x2 up to xp t x1 x2 up to xp is the determinant of order n by 1, n plus 1 by n plus 1, and that is your kernel k k x comma t, then k x comma x1 twice k x comma xp, then k x1 comma t, likewise we have here k xp comma t, this is k x1 x1 k x1 comma xp, k xp comma x1, and finally we have k xp comma xp, means your control values is determinant. Okay, and again we have this k x1 x2 xp and x1 x2 xp. This is given by again a determinant for the p by p, not like here we have p plus 1 by p plus 1, and here we have p by p, and this is k x1 x1 k x1 x2 k x1 xp. If I separate directly here, or that is also k x2 x1 k x2 x2 k x2 xp, and here we have k xp x1 k xp xp. And here you in short, suppose you want to find k of x1 x2 x1 x2, you have to find this determinant of order 2 by 2, and that is your value of this k, right? And then let me write that cp is also, we have this small cp, c0 we have taken to be 1, and small cp is integral p integrals k of these determinants x1 x2 xp x1 x2 xp, and you integrate this with respect to x1 x2, and similarly your capital CPs and this way x comma t, again those are the integrals of the other determinant xt x1 xp x1 dx1 dx. So this is the data what we have, and by using this data we have to find the observable kernel by using these determinants. In short, we have to find these determinants k and all this, then we have to find the values of this ki's, and then we have to find the values of this dxt lambda and d lambda, and then we have to find the observable kernel. In short, this is the way, right? So in our case, here we have kernel k x comma t is given by x into e raised to p. This is our kernel. Okay. Now we have to find CIs, right? We are not using any regular expression here. We have to find small CIs and capital CIs. So to find capital C1 of x comma t, it will be p is equals to 1, so only one integral, and limits are 0 to 1, 0 to 1, and then we have k of this capital, so x x1 t x1, and then d x1, and this is an integral. If you want, you can find it separately or you can find it simultaneously. So in this case, we will write directly 0 1, and this is the determinant of k x comma t k x comma t k x comma x1 k x1 comma t and k x1 comma x1. So to find this value of determinant, and then you integrate that with respect to x1. This is equals to integral 0 to 1. You put the values k of x comma t is x into e raised to t. So this is x e raised to t. This will be x x1. So it is x e raised to x1. This is x1 e raised to t, and this is x1 e raised to x1 determinant. You integrate this with respect to x1. When you evaluate this determinant and when you find the value of this integral, you can check. This will give you answer 0. This you can verify. Okay. Similarly, when you find the value of capital C2 of x comma t, let me just write the formula. This is integral 0 to 1, integral 0 to 1, a is capital C, so x, x1, x2, t, x1, x2, and dx1, dx2. Again, this will be the determinant of order 3 by 3. Then you find the value of determinant, you evaluate, and then this double integral, you check the values. Again, let me directly state this is again equals to 0. Right? And similarly, you can go and say that Cn of x comma t is equals to 0 for all n greater than or equals to 1. Because C1 you got 0, C2 you got 0, and likewise you can check and say that Cn is equals to 0 for all n greater than or equals to 1. And definitely we have said that C0 is nothing but our key, the kernel key. So this is all about your CIs, that is capital CIs, that will help us to get this value of capital DXT lambda. Let us take this small CIs. Okay, so now C1 is nothing but integral 0 to 1 is small, so k of x1 here dx1. This is nothing but, and we will check what is this, 0 to 1 k of x1 dx1. This is integral 0 to 1 x1 into e raised to x1 dx1. And when you evaluate this integral, you will get the answer as 1. Okay, to find C2, you have integral double integral 0 to 1 k of x1 x2 dx1 dx2. Again, you get the value of this determinant, substitute over here, you integrate it, you will get this is equals to 0. Right? And then hence all when you evaluate other ones, you will get equals to 0. Right? Find the value Cn equals to 0 for all n greater than or equals to 2, not 1. C1 is equals to 1 here, and again C0 is 1. That's what we have stated. So with this values of capital C's and capital small c's, we will have dxt lambda is equals to, let me show you again, dxt lambda is kernel plus all the ci's, and just now we have stated that all cp's are 0, that means the summation is 0, and only you have kernel and your kernel is x e raised to t, and hence here your dxt lambda becomes kernel, and that is nothing but x e raised to t, and t lambda is nothing but, again show you what is t lambda, 1 plus the summations We got only C1 which is non-zero, which is 1, the rest all are 0, and when C1 is there, it is minus lambda upon 1 factorial is minus lambda. So 1 minus lambda. And hence we will have here it is 1 minus lambda. So if you have these two quantities, we can easily say hence the resolvent kernel is gamma x t lambda is equals to d x comma t comma lambda divided by d lambda, and here we got x is to t divided by 1 minus lambda. So this is what the question was. You have to find the resolvent kernel, and we got the resolvent kernel. If you want to find the solution, it's very simple. You write y of x equals to fx plus lambda integral, and this is resolvent kernel ft dt. Okay. So how this method is clear, let me put some examples for exercise. Find resolvent kernel and solution of, that means once you have resolvent kernel, just one step further and you can write the solution. And solution of, write the integral equations here. 1 y of x is equals to fx plus lambda integral 0 to 1 x plus t y of t dt. Second, y of x is equals to d raised to x plus lambda integral 0 to 10 1 0 xt by t dt. Third, y of x is equals to sin x plus lambda integral 4 to 10 x by t dt. And fourth one, y of x is equals to e raised to x plus lambda integral 0 to 1 2 e raised to x plus t by t dt. So if you have time, you can solve this by using both the methods. You can go for the iterated these iterations, that is recurrence relations for CIs, and secondly you can find the Fredholm determinant and get the result of CIs, and then you can write the resolvent kernel. Right? Let me state the Fredholm second theorem. Third theorem we can check. I will just state the Fredholm second theorem, and proof we can see Fredholm's second theorem. Okay. Now this is the statement: if lambda 0 is 0 means the root of multiplicity m of the function, it is your determinant d lambda of the function d lambda, then the homogeneous equation y of x is equals to lambda 0, this particular value of that lambda 0 integral a to b, and if we are talking about the Fredholm's theory here, a to b k x comma t by t dt. So this is at least one and at most m linearly independent solutions. I don't have to speak on the linear independence of functions. Linearly independent solutions that here I don't know whether can write. See, yi of x is equals to dr. Now this r, this dr is called Fredholm's minor. I will write it afterwards. dr Fredholm's minor is x1, x2, x3 up to xi minus 1, then x, in between there is x, and then xi plus 1. So at the ith place we are putting x. Remember, at the ith place we are putting x. This xi minus 1 is here, where there was xi we are putting x, then xi plus 1. And then here again 3 t I minus 1. At ith place you put t, then ti plus 1, and tr, this tr, and you evaluate this at lambda equals to 0. Right? Now here your I will be from 1 to up to r, and your r is from 1 to up to m. So it is at least 1 or at most m solutions here. Right? Let me write this r again properly. R. Okay, and further, this is not identically 0. Not a 0. Okay. Any solution of this, right? Any other solution of this equation is a linear combination. Again, you know what is the meaning of linear combination? Linear combination of these solutions. So if you take any other solution, it will be a linear combination of the given these solutions. Okay. Now, as I said here, this dr, not the dr is called Fredholm's minor. And that what is that? Here, and here. So dr or anything dn of x1, xn, t1, tn, you can put n or r, it's the same thing. That is equals to this k, you know how to find k of x1 up to xn, t1 up to tn, plus write down, plus summation p from 1 to infinity minus lambda raised to t divided by t factorial, and then as in last cases there are t integrals limits a to t b to b assumed to know k of x1 x2 up to xn again down t1 t2 up to tn, and then apart from this you have z1 z2 up to zp z1 up to zp, and then this you are integrating with respect to d z1 d z2 d zp, right? Some module here or this is here, right? And again let me see what is this xis and tis in the next page, where this xi and ei are two sequences of arbitrary variables. Proof we can check, and again we can check the third term as well.